Ed, welcome to the Universal Calibrating Machines webinar. Glad everybody is here. Some minor logistic issues this morning, but I think we're through most of them. So, people that do not know what we do, we manufacture force calibration products such as the Morehouse UCM. We provide force measuring equipment, calibration service using international standards. These standards allow us to lower uncertainties of customer equipment, and we enable our customers to make better measurements, which makes the world a safer place. So there's this thing called global consumer risk, and if I give or Morehouse gives a bad measurement to one of our customers, and then they go and measure more and more devices, guess what happens? It affects the whole chain of calibrations. So when we look at this and we look at the UCM and we look at everything else, we want to make sure we make the right measurements, and that includes adapters. It includes having standards with low enough uncertainties, competent technicians that know what they're doing and talking about. And that's why we like to give these webinars and educate people, because we're not infallible. By no means are we. I think we do things really, really good. Can we do things better? Yes, and we're constantly improving those things. We're building new machines, new equipment, investing in some new electricity, and maybe even adding on to our building to put everything together. So our purpose, why we do this, is we like to help other companies. We feel if we help them, we give these webinars, we create a safer world by helping companies improve their force and torque measurements. And that's at documents and settings, documents and tools on our website page, that if you go to it, all this stuff is free, almost everything, besides our book on Amazon, which is $4, and you can wait anyway and register for anybody that hasn't done it. You can register for our book or our newsletter, and then you can get links for our new ebook, which adds another 80 pages to the already existing one. So it's like a 200-page booklet on everything that I've learned about force calibration in the last 25 years. I try to document as much as possible through the blogs and everything else. So what makes us different or unique is we have dead weight. We are a primary lab, which means we offer dead weight calibration. So being a primary lab, we offer calibrations with super low uncertainties, like 20 parts per million of applied force to 120,000 pounds of force, or a little over 500 kilonewtons. And we also go up to 10 meganewtons within 0.1. And 10 meganewtons is about 2.25 million pounds of force. So really, really high level force. Primary lab up to 500 plus kilonewton or 120,000 pounds. There's me. That's an old picture. If you want to reach me, anybody can have copies of this presentation after it's done. You can just click the links. You shoot me an email if you have questions. I'm happy to answer them. You can follow us on, like I said, social media, LinkedIn, Facebook. If you LinkedIn Messenger me, people know I respond to that as well. So outcome, why are you here today? Hopefully you're going to learn something, and hopefully you're going to learn about problems that exist when calibrating force measuring instrumentation, adapters that reduce errors, and how to get the best uncertainty from a Morehouse Cal machine. So we are a for-profit company, so we are, even though we do a lot of this social, what I consider to create a lot of social value, at the end, we still want to create some economic value back to ourselves. So agenda, calibration headaches, typical error sources in force calibration, and adapters that reduce errors and UCM uncertainty. So headaches. One of the major headaches is customers. You start a force calibration lab and customers want to send you stuff, and you want that stuff because you just invested in equipment and you want to make money on that equipment. So, but when they send you stuff, you might not have the right adapters to calibrate it. And now that creates a dilemma. We've been in this business for over 100 years, and we still see instrumentation come in today where we do not have the adapters. A lot of times that's not the case anymore for force. It's more so for torque that we do as well, though it's still for force. Someone makes a new load cell, a different thread that we haven't seen before, a new widget, and we need to figure out how to calibrate it. So with that, it starts by asking a lot of questions to the customer, right? Well, how do you use it? What do you use it with? All of these things. If we get all these right, we can start formulating how we have to fixture it in our machine to calibrate it. And we're going to dive deeper into that. And we're going to dive deeper into these calibration headaches, like right here, problematic setups, missed revenue opportunities, costly reference standard dual calibration modes, unidentified errors, time-consuming rework, assumptions about your calibration accuracy or uncertainty. This is often, quite a big one here, as far as this goes. And I'm looking for my pen, but if I don't have it, that's fine. But these setups here are problematic, right? They can be problematic. This one, if I'm calibrating a button load cell using this method, just a flat plate, I'm going to get a different result, maybe not so much as repeatable if I use adapters that are better for centering. This dynamometer, we're going to talk about this here. It's supposed to read 50,000 pounds of force, and it's 860 pounds out. Then when we talk about dual mode calibrations, look, our competitors make these machines. They have their function. They work. They can do compression, tension in the same setup. But we're going to talk about this. Maybe if we don't get that setup right with the adapters, we could have error sources that are much larger than the uncertainty we claim. And if we don't get it right, what's it lead to? Well, maybe it leads to rework. If we're an honest company, then it does. I mean, there are people that just shove everything under the rug and just say, oh, yep, I'm not going to do a recall. I'm not going to do this. Hopefully no one's in this group of people are like that, but it happens, right? And you make the decisions when you have those out of tolerance conditions. No one wants them. But sometimes if we've done something wrong, we have no choice but to bring it back. We just had one. I said, like, we are not infallible. We had one that happened just the other day. We used the wrong set of weights that were supposed to be used for torque and didn't correct for it. Even though there were notes everywhere and things, we just missed it. So now we're recalling it, and we're gonna do it right. But it happens, and it happens to almost everyone. So. That being said, I got to pull out my drawing tools now. So you're all experiencing what I wanted to do is go draw, and now I couldn't change my slide, and now I have to erase them because I'm using ones I don't normally do. So anyway, I'll admit it. Hey, there's people that need to be trained on how to do webinars when they don't have their normal setup that they're used to because they thought they had it before they logged in. That's me. So I was talking about flat to flat and versus using the right adapters. Here's a problematic setup. This instrument comes into the lab and we use it. We do the calibration, and you can see here, I'm going to go back to my pen and drawing tools. You can see here, this is on the left. And what we're looking at is when we did this cal, look at the deviations. And we rotated the load cell around, and then we had such large deviations. And the standard deviation was 10, this is pounds force, 10.69 pounds of force, maximum deviation of 21, and then an error related to that of 1.045%. When we use these adapters, and these adapters happen that we designed and we made, if you get me on a tangent, I'm going to say, hey, load cell manufacturers, and we're included in this group, are a bunch of idiots sometimes because no one standardized anything, right? This load cell here should be pretty simple. Any 5,000-pound button load cell, why didn't they make the same button, the same base? No, every manufacturer made it different. So we have a lot of adapters for a lot of different load cells, which is costly. And somebody complained to me the other, in one of my training classes, said, why are your adapters so much? Because we're not in the business of making, no one's buying, 500 of these adapters. Typically a lab might have a need for one, and we might get an order for one like every 2 months. So for us to do anything but single piece flow and make a large quantity that could drastically reduce the cost doesn't make sense. If industry would have standardized all their load cells and all their thread sizes and everything else, then maybe we could make 100 adapters at a time and sell them much at a much more cost-effective price for everybody. That's just not the case. It's not how industry is, and it's a lot goes back to the manufacturers and lack of standardization. Though when we did use the right adapters in here, getting back on, look at the deviation. We went from 21 to 4, and the max error of 1%, we got to 0.2%. Now, the problem with this is, and Patrick's been through these courses, is a lot of people expect better than 0.1. Just not going to happen with this type of load cell. So just want to make everybody aware of that. And I'm having big time problems using the tools and the GoToMeeting. So anyway, other thing, missed revenue opportunities. Not all machines are created equal. Morehouse has designed the UCM to accommodate almost all force instrumentation, from crane scales to button load cells. And those that cannot be calibrated, such as aircraft and truck scales, we have this solution, which is our USC 60K press here to the right. Though, think about it. I showed you when you start thinking about, hey, I'm a lab, I want to be able to calibrate all this instrumentation. You need to start thinking about like what that entails, because a lot of customer service reps or salespeople will sell you almost anything, but it might not be. You might find, hey, that machine that I was thinking about, even though it's cool, automated, and does all this stuff, it doesn't have enough room to do 80% of the stuff I want to do, because 80% of my customers are general industry using crane scales, dynamometers, and the like. So you really have to evaluate those types of things. Then there's this other machines, universal testing machines, which people use for calibration, and maybe they shouldn't, maybe they can. This is a trade-off, right? It's a materials test machine, and it's used to test tensile strength and compressive strength of materials. Most of these machines are designed to be 0.3% through 1%. Very few labs can calibrate other force measuring instruments to better than 0.25%, 0.25. This number comes from E74, assuming the device was calibrated uses a Class A verified range of forces. So essentially, these machines might be good enough to do the cal. You really have to talk to the manufacturer and know the manufacturer and figure out, like, there's some manufacturers that will tweak them, that if you know you're going to use this for as a calibration standards, that they can really tweak and adjust the control. Then you need to have your force instrumentation likely calibrated by primary standards dead weight back to do calibrations in accordance with E74. So the dead weight would assign a Class AA verified range of forces. Lots of stuff there and lots of terms. But what the takeaway is, calibration capability on these machines is typically above 0.3. It can be used to apply force with a well-defined reference standard calibrated by primary standards. And if it's used with a load cell, where I really wanted to make the point here is, you have this machine, it's controlled. You almost need to buy, in I think almost all cases, you need to buy an additional reference standard load cell, because the load cell that's in the machine is your control load cell, and then you buy a reference, have that calibrated by a reputable laboratory, and use that to make measurements. And then a CMC of 0.5% may be achievable, but there's a lot of hurdles that you have to go through to get there, and you have to do it right. I'm more than happy to help people get that right, because what it amounts to is, likely you have the machine, it amounts to adapters and either purchasing a load cell from us, and then we calibrate it with dead weight, or sending us a reference load cell to be calibrated in dead weight with primary standards. Dynamic calibrating machines, that's what I call these. CMCs, they can do compression, tension in the same setup, usually automated, space is sometimes limited, and they are not suited for calibration of all equipment. They can calibrate quickly, but they have different timing profiles, and a lot of the standards, ISO 376 requires the force to be held for 20 to 30 seconds, and they don't do that well. They can change the programming, but most people that use this are flying through the test points and not dwelling on them. That comes from my biased opinion of talking to people at the ASTM committee meetings and stuff. How do you use these? How do you do this? And I get answers, well, we just go straight through the cal till we hold things for about 6 seconds on a time frame. So very different answers than the 20 to 30 seconds that ISO 376 requires. They also tend to cost 2 to 3 times more than a comparable UCM. The reoccurring calibration cost is higher as they require the reference standard to be calibrated in both tension and compression. And if the only requirement is for production load cells, they may be an excellent fit. Hey, if I'm manufacturing load cells for an industry like scales where I'm making, load cells for $5-10, if I'm manufacturing any line of load cells that need more of a commercial calibration, quick check to nonlinearity hysteresis, and I want to do, 5 or more an hour, hopefully I can do 10 or more an hour, this machine might be an excellent fit because I can just put it in, run it, technician can record the readings, and then I can fixture the next one in, and same setups, you can just bang out work. Really, really easy. And one of the best tests to determine if the calibration and measurement capability uncertainty component is within the claim uncertainty. People are not doing this as much. And if you have one of these machines and you're claiming a number, or a lab is claiming a number such as 02, 05, whatever, the best way to prove it is to do an interlaboratory comparison or proficiency test. So that will let a laboratory know of their true capability. And we offer ILCs and PT options. So then we get to the title of this webinar, the Universal Calibrating Machine. It's a versatile, easy to use machine for compression and tension calibration of force instruments. The machine matches the accuracy of the reference standard. There is some additional uncertainty that needs to be accounted for. Most machines are aligned well enough that the maximum amount of side load, per load cell spec sheets, is about 30 parts per million. And then typically we find, I tell customers and I help them with uncertainties, is typically they're getting better than 0.2 to 0.3%. Some will go to 0.4, and it depends. So if you want to get better than the 0.3 to 0.4, like I have listed here, 0.2 to 0.3, it's going to take some technician training, some really good reference standards, repeatability when you do your repeatability studies, and it's very obtainable with time and practice is what I want to say. But most labs are typically between they're edging closer to 0.3. And the other reason for that is they're not making multiple standard changes. The better you want your uncertainty to be, going back to Euromet Guide CG4, ISO 376, and some of the others, the better you want the uncertainty to be, the more standard changes might be required. So if you wanted to maintain something like 0.1, you might need to buy 3 or 4 load cell standards, where if you wanted to maintain 0.2, that might be 2 to 3. If you want to maintain 0.3, 0.4, you might get away with just 1 standard. So the benefit of 1 standard versus 2 is doing a full calibration without changing standards, and that reduces the time. So if you're willing to spend more money on standards and spend more time per calibration, you can drill that number down. Most people find that happy medium, again, around the 0.3%. So yeah, and as it says, a load cell standard with 2 or 3 load cell standards, 2 to 3 to more than likely 3 to 4, it can be better than 0.1. So what makes a good force machine? If you want to design your own, we've been doing this for 70 plus years, and I can tell you that it's plumb, level, square, rigid, and free of torsion. Get an engineer that can design something that you do the trade-off of how thick do I want it? Well, if I go 3 inches, it costs me this. If I go 2.5, it gets me the bulk. It eliminates the majority, keeps it as rigid as possible. So that's another trade-off. I mean, what we've done in the past few years is all of our machines now are magically, like in some cases, 1/8 of an inch to 1/4 of an inch thicker on the platens, and that's just to increase the rigidity. It's a cost. You start valuing what type of material lots can I buy, and how can I, because all of this stuff is machines. So you go with the best you can to get that rigidity, but here pictured right, we have 100K UCM, the upper and lower platen are ground flat, and adjustable feet allow the end user to obtain level condition. If level is not achieved, errors from misalignment will happen. So really important, those feet, they look pretty generic to me sometimes, but it's really important to get everything leveled as straight as possible because it will make your calibrations as good as possible. So easy operation. You have a pendant switch for the most part, and it's always that diagram on the right shows the hydraulic cylinder is always going up. So you fixture your instrument in compression or you fixture it in tension, depending on this. And the reference standards, like I said, when we said costly dual calibrations, it costs more to have your standard calibrated in both tension and compression. When you switch from tension and compression, you really need to re-exercise the load cell. There's some other things with the process that may help you get better uncertainties if you just keep a load cell in compression only throughout its life cycle instead of both compression and tension. And then reduced errors from misalignment. That's the way we have it set up. We have it set up so the way it sits in that machine is exactly how it's calibrated with those adapters and ball adapters. And we have a lot of videos here for if anybody wants to learn more about that. Now I overwhelm people with all the errors of force calibration. And there's a lot. Proper pin size, which we'll talk about. I went calibration of button cells. The same applies for calibration of washer cells. You just read that using mass weights instead of force weights. Lots of blogs on that topic. There is a new Excel sheet that's available for download at the documents and tools section. That Excel sheet can do your mass to force and force to mass conversion we've added with air buoyancy corrections and material density corrections, because a lot of people forget to do those too. They might just do gravity only, which only gets you part of the way there. Cable length, all kinds of stuff here, timing errors. If you're interested to learn all about them, our ebook, the new ebook version 2, and we have a force class that could be good. But yeah, you can look at typical error sources, not exercising a load cell, mass weights, pin size, traction dynamometers, all here. At the top of this, you have an uncertainty budget, and then I have all of these that I could add any of them back to the budget, which would just completely blow up the budget into several times more than what is shown here. So another common error sources, not bolting. If you're going to bolt a load cell in place, a practice I do not recommend, but some people do. They take it out of a machine, they send it to us to calibrate. So we're going to follow the manufacturer's specs, and we're going to use a star pattern. Another error source might be batteries. Somebody sends you stuff in with a low charge. The meters might not be regulated, and you might get a different output than if you used fresh batteries. So in our lab, we have Amazon Subscribe and Save, the plug for Amazon. We have batteries coming monthly, and we just put new batteries in everything and calibrate them with fresh batteries, because that's more repeatable than saying, hey, I've discharged my battery X, and now you need to, for you to match my cal, you need to be on 80% likely, because at some point the batteries are going to stop working. And but then we have not following published standards there. There's some sections of E74 where you shouldn't have a force point below the first non-zero point, and that data shows that someone reported it. That's a big no-no. And then we have loading through the bottom threads at the bottom, all error sources. And then there's adapters. You buy a calibrating machine, the next step is, what am I going to calibrate? I'm going to need adapters. So force calibration is very mechanical. Keeping the line of force pure, free from eccentric forces, is key. And different adapters can change the alignment and the amount of strain. Some of these error sources that we could have is shown denoted by red. We have incorrect loading condition. That's thread depth, which I can talk about. We have videos. A lot of the time that we get some information from a customer and they say our results do not match yours, typically it's this thread depth problem. They haven't locked something in. They're loading it. Maybe they're engaging half instead of full. there is a big difference. We highly recommend locking an adapter into place, and then you have the hardness of top adapters, and then the improper pin size, all of which we can discuss some of. So there's pin size. You can see picture on the left, 49-140. Remember I said 860 pound error earlier. That's 1.72% error on a 0.1% device. And that's from not using the proper load pins. At the bottom there, we're showing a bent rod end. This is something that someone might take. Here, we're at fault on that grade 8 bolt. We used that machine grade 8 bolt for years before it failed. And then when it failed, we did an analysis, and one of the machinists undercut it just a hair. And that little bit of a hair made it fail probably after about 100,000 load cycles from what we were thinking. But it failed. So now all of our adapters, we went through about 5 years ago and started, and anything where an engineer or somebody just made a custom piece is gone. They do not exist, or they should not exist. You should have to really hunt for them in our lab if we're doing numerous cals. That's not to say we don't still have some homemade adapters. The homemade adapters are typically for one-off instrumentation, and if it's deemed unsafe, it was remade. So there's a picture of a collapsed bridge. Things that happen when you don't get measurement correct. I believe that one is because of a too thin gusset plate. It was spec'd, and over time, what happens over time, things corrode, things wear. When things aren't spec'd properly, like these adapters are grade 8 bolt, eventually they fail. And when they fail, catastrophic things happen, unsafe conditions. Your technician is probably going to want to go home and change their underwear if they have a grade 8 bolt break at 100,000 pounds of force. It happened to us, and it is never exciting. I've broken several things in our machines, and it wakes you up pretty darn quickly. And now I'm hoping that we don't have any breaking because we've redone all our adapters. But in the past, when I first came here, we were also guilty in the 99, 2000 of using rod ends and some other things that now is all gone and thrown out. Tension links, talking about the pin size. You look at these diameters. What we want to look at here is the E, the shackle pin diameter. And that's on our drawing, which I've determined that I don't have my good drawing tools today, so I'm not going to fiddle with it. But if everybody can see E, it's called out shackle pin diameter, then look up at E. These are the pin size that the manufacturers recommend. And if we look at them, larger view of it, you can start seeing this, that, hey, 20 ton is a 2-inch pin and 25 ton is a 1.97-inch pin. We make clevis sets and adapters. This set, our goal here is to save money. They're not inexpensive, but what people were doing is they were making a clevis and a pin for each of those different sizes, and there were multiple just on that drawing. And that was a lot of adapters. So he said, there has to be a better way, quoting Shark Tank, right? There has to be a better way. So what we did as an engineer and I sat down and we designed this set and we got it patented. It's one of my patents that I've had while I've been here. Very proud of this. It took 3 months of us looking at all the manufacturer's stuff, figuring out what was uniform, what wasn't, what rollers we needed to make, what's going to get the majority of instruments that have these different pin sizes, and we made the kits. So, and the solution is big proponent of lean manufacturing and some of the lean processes, and we wanted to make the setups easy for the technicians. So the adapter solution here is quickly switch to calibrate a different instrument without disassembling the entire setup, which improves accuracy and workflow. And you can see here by the different drawings, we have 2 value kits, a clevis value kit and a tension member value kit. And it just comes with the whole set. So if you're new to Cal or you're buying a machine and you think you're going to do tension links, these are the sets that are recommended. Because like I said, you just do not, and load cells, you just do not know what's going to walk in that door at any time. Hard blocks, we showed this. I've present this. This is this is probably the number one. This or the tension link ones are probably the number one slide in every presentation I give, because it's so dramatic. The tension link, a 0.1% device, use the wrong pin, and you're out by over 17 times specification. Different hardness of top adapters. This one, if we're looking at these cals, people are expecting better than 0.25 typically, and we're 10 to 12 times that. Just looking at them, just really rough math, right? 0.025, 0.3, right? That's 12 times the error from just using a different hardness of adapter. So people ask, what do I do? Well, it's the simplest solution. When you're buying a load cell, you buy an adapter to use on top of it, and you marry that to the load cell, and therefore, whatever happens, as you work hard in it, as you go through 10,000 load cycles or whatever, it changes with the load cell. And it's so slow and so gradual that you keep getting it calibrated, and over time, it becomes more asymptotic, which means it just straightens out. You don't really see it anymore. But if you send a load cell in, one of these like single column high stress load cells without a top adapter, and we perform a calibration, use one of ours that's like 44, like a Rockwell maybe 44, and you go and use a softer material, you better believe you're going to have a significant difference in the output. Now, shear web load cells do not behave this way, but these single column high stress load cells do, and as do multi-column cells. So another thing, this is our concrete kit with top and bottom adapters. You want the bottom adapters because if you have female holes in the bottom of the cell, it's going to mark the platen. And the last thing you want to do is go into calibrate a customer's machine and mark it up. If you buy one of our Universal Calibrating Machines, you want to have adapters to protect it, because as soon as you mark things up, you get uneven surfaces, which are no good. So this is a set that has everything with it to protect machines. So I talked about the thread depth. Here's the cell. People sell these. I don't like ever selling them without an integral adapter installed, and this is why. Right? This load cell, here's 3 different adapters threaded against the shoulder, and you can see the max error is 1.7%. The customer requesting the cal wanted an ASTM cal, and they're expecting better than 0.25 at capacity. So pretty significant error sources here, and they go unnoticed. You can send them to your local cal lab. They do a cal, they report it. Next year, you send it back. You look at your data. Hey, not much has changed, but you're using something different than what they used. You're never going to see it. You're going to perpetuate those bad measurements and create one of those global risk scenarios where you're passing it on because the lab passed it to you. Hey, you sent it to us. We used our adapter, and we didn't have a conversation with you, and now you're doing something completely different than the way we calibrated it. It's problematic, right? This is why on that contract review, we try to ask all the questions. It is annoying to some of our customers because there's so many. How do you load it? Can you send the adapters? Is it compression tension? Is it ascending, descending? Do you want this? Do you want that? Do you want a commercial cal with nonlinearity, hysteresis, SEB, or do you want it set up to be direct read with a conformity assessment? Do you want ISO 376? Do you want ASTM E74? Are you using adapters with it? How are you setting it up? Are you thread loading through the bottom? Are you loading it against the shoulder, or are you threading something into it? All these I can go on and on. I could take an hour to ask you all the questions. But yes, so it's important to have the discussions because these errors are quite large. So the solution, this one's simple. I need no discussion with anybody if you lock the adapter into place, right? It limits my discussion on adapters. It's like, do you load it? Any chance? Do you load it flat against the base? Yep. What type of cal do you want? I want a ASTM cal. Fine. You want compression only? Yep. Ascending only? Yep. The list of questions is a lot less. Or you pick a top adapter and always use it with it. And then you say, hey, I thread this into it. I thread it against the shoulder, hand tight. All right, hand tight's different for me than it is for you, though at least we can mitigate the error. Another thing, we're going to put these in the cal machine. We're talking about, it's still a universal calibrating machine webinar, but we're talking about how we mount the load cells and how we calibrate the load cells in the cal machine, or the dynamometers and the pins. That's what we're relating back to. So here, the one on the right would be how we mount a reference standard load cell, and the one on the left would be how you would mount your unit under test or device under test in the machine for compression. And we're recommending alignment plugs to center the instrument that should go up into the load cell. And then bottom rings, if you don't have an alignment plug or the manufacturer didn't have them, these bottom concentric rings allow you to use a scale or another tool to center these instrumentation as best as possible. So it's highly recommended. And then if you're doing a lot of these button or washer cells, I showed you that increased performance that was like 525% better. Remember the 1% to 0.2%. These types of adapters, and they're a pain because you're making, these adapters are heat treated. There's a lot to them. They're not just simple things that I said we could make, 100 of. We'd love to make 100 of them if the demand were there, but all these load cells and manufacturers of these adapters have decided to do different sizing, and that means you might, even a bottom adapter might work for one load cell, but the top adapter is going to be different because the piece that sticks out there is going to have different diameters, and we need to match that diameter with that top adapter. Then we have things like the PCM, L brackets. People make the handheld force gauges. Again, if someone just made a common centering distance on these handheld force gauges and they made common bolt patterns, you wouldn't need all of these back plates and all of these adapters for centering distance. But we have a kit. These can be done in the UCM. Shown here, they are done in the PCM. Our portable calibrating machine that goes up to 2,000 pounds. And if you have this kit, you should be able to do almost any handheld force gauge that comes into the lab. And then there's the PCM calibrating load cell to load cell. Can be used. High capacity. This is a big UCM. This is our million, our 2.25 million, which we go to 5 meganewton in tension. This is that setup, right? Huge machine. And we get into custom here a lot of times. Different manufacturers, like really good old cells that I've seen used have like 8-inch threads. Complete overkill for 1.25 million, but they exist, or 1.2 million. And safety and quality control becomes even more important at large capacities where mishaps can be life-threatening. Yeah, if I pull something apart in a dead weight machine at 100,000 pounds in tension, it makes a loud bang. You might need to re-level the machine. Everybody's going to hear it. Things can bend. It's a pain in the butt, but generally, injuries do not occur. If you pull something apart at 5 meganewtons in tension, stuff's going places. That's a lot of force and a lot of energy, and it's not something to be toyed with. And we've designed adapters up to 2.5 million in that can be used. It's just dotting I's, crossing T's, and doing a lot of testing. Adapters conclusion. If you're running a cal lab, communication with the customer is key. Unfortunately, it does not always happen. Things that happen, you deal with third-party suppliers that have no idea. Someone told them just to go get a calibration, and they're calling up looking at a place that can do a calibration, and maybe their criteria is I need it done in 7 days, which we typically have a 7 to 10 business day lead time. But then they don't have answers to the questions. So then you get equipment in and you need to talk to the end user, and that's difficult. Purchasing departments. Yeah, like I said, someone might not have the ins and outs. Technician or management said, hey, go get this calibrated. They might not talk to each other. You have management that doesn't care. Just find me a place to put a sticker on it. And then you have large companies where people look, the work shortage, keep reading, there's 0.6 workers for every job open. And in a large company, they might have turnover. The person that knew might be gone. And that could happen in any company, really. And that becomes a problem. We take notes and document everything. It's a good practice. So if we have seen a load cell before, we have our own internal wiki, and the technicians will make notes everywhere on how we did it. So if a technician would leave your company and you had it done before, we would do it the exact same way we were instructed. We should ask, has anything changed? And typically at that point, well, I don't know. I'm taking over, and it's a whole mess. So, but ideal solution is always to calibrate any force device with the adapters that are being used. And the next best option is to buy Morehouse adapter sets. I kid, but it's true, is to buy the adapter sets, because then you can at least document what you did. But I need to stress that the best way is to do for the customer to send you the device exactly how they're using it with their adapters. If you can't do it, the next best option is to document what you've done, i.e. our adapter sets should best replicate, in most cases, best replicate, like with the pin size and everything else, that of the manufacturer. We have a technical paper that goes into more detail about recommended compression and tension adapters, because I just really scratched the surface on this. So I'm going to ask, there's people in the chat window here. We have, I'm going to ask, instead of, because I couldn't load the poll, what people think. What should I do with older adapters? Should I visually inspect all adapters for signs of wear or fatigue and replace if they show any signs of failure? Spend a lot of money to have them tested frequently, because that's a trap we can get in. I can send them out to have them x-rayed and tested and all kinds of stuff. Should I continually use it until it fails? Replace adapters that have been used for more than 20 years or 100,000 load cycles? These are, questions. If you have answers, I think for the most part, the answer is pretty obvious. So hopefully people, I see some answers here. Yeah, as it's coming through. A and D. Let's
trade them in Morehouse for a discount.
Yeah, thanks, Tanner, on that. Yeah. So no, if you buy, Tanner knows, if you buy adapter set, we're always trying to work with people on this. I like nothing more than to have people call us and piggyback off of somebody else's orders. I'd love to get a group together, because we can save money on our setups, and then we don't have to run the single piece flow. We can run more, and all the money, anybody that operates a machine shop knows the majority of money is in initially purchasing what you need, so you have the raw material, cutting the raw material, and then the setup in the machines. So if you can get that set up, load your programs, running the second one is so much more cost effective than just running one. So anyway, yes, A and D. UCM uncertainty. So we're going to break. So you bought a cal machine, you got the adapters. Now I'm ready for uncertainty. And we often get the question, what is the best uncertainty I can achieve? And I went over that earlier and said the expectation generally 03 to 04 for newer labs. If you start getting experienced technicians, you get the 02 to 03. But we wrote a paper, and the paper basically said, hey, if I operate, I need a standard change about every 20%. And if I'm willing to do that, I can more than likely narrow in on 0.02%, because that's what we did, and that's what we got. We replicated it. Of course, our technicians have been doing this for more than 5 years. So there is that learning curve on how well they can hold the force, how well they can hold the machine. There is automation coming out. It'll be out next quarter for the machines. So I should mention now that is going to be a universal upgrade. If you already have a machine and want the automation package, we can do that. Automation should hold the machine to better than 1 in 50,000 counts. The target's 1 in 100,000, but I'm setting more of a realistic expectation instead of stretching it to 1 in 50,000 counts should be what's expected. And then we have several factors that we need to look at, significant contributors to measurement uncertainty. And this is from that paper, and there's the link from the paper. But if we're looking at things, we're looking at our reference standard, the resolution of the reference, the resolution of the unit under test, the UUT repeatability. I want to test my techs. I don't know what technician's going to see an instrument. I mean, I can't always assign it to Tanner, the best guy in the room right here, to always do the cow, or Patrick. I need to go. I need to go on and get what happens if Joe does it, or Bob does it, or Sally does it. All this. So I really should be doing R&R between techs to see if there's a statistical difference between my by with any of my techs. And then I'm going to look at year-to-year stability. I'm going to look at my environmental factors. How well do I control the temperature and everything else in the room? I'm going to look at side load sensitivity. What if I have a little? What if I'm off center a little bit and I have a little bit of side load? So some of that's going to show up in ILC, but I want to get it there. I have a belief with uncertainty. 99% of the time, here's the uncertainty statement that's gonna baffle everybody, but 99% of the time, I think it's great to be conservative, to give yourself a little bit of fudge factor. And then people say, what about the other 1%? Well, the other 1% is evaluating what matters and what doesn't matter. And sometimes, for example, one of our dead weight machines that was done, one of the weights in one of our dead weight machines has more bias than the other ones. And if I claim 20 parts per million on this dead weight machine, I'm in. I give myself, when I use that weight, I give myself no wiggle room. But when I use any other weight in the machine, I have a ton of wiggle room. That 1% is for us to have identical to the 0.002% on our 30K machine. I need to apply a force of 3,700 pounds. I have yet to apply 3,700 pounds of force to any instrument, because most instruments are 30,000 capacity. So I'm going to do a 2% point in steps of 3,000, 25,000, 20. 3,700 never comes up. So this is why I guard myself on the 99%, because most of the time, I'd rather claim like 25 parts per million. If I had a lot of weights with bias and a lot of combinations with bias, I'd rather claim 25 parts per million and give myself wiggle room all day long to not have an alloy tolerance. But on that 99%, you evaluate everything and say, what are the odds that 3,700 pound force, I'm going to use that a lot. And then if I have an out of tolerance condition, I'm going to have to go back and evaluate everything and see if it made a difference. And I'm willing to live with that risk. So that's the 99%. Very strange discussions. You got to kind of be in my head a little bit for that. But I tend to err on the side of conservative on all of our other machines, except for our 30K dead weight with that 1 point. So that one, I'm not really to bump everything up to 25 parts per million just because of that. Anyway, so how does uncertainty work? It's measurement uncertainty data is cumulative from one level to a hierarchy. We're looking at measurement traceability, which Patrick, who's now an assessor with A2LA, should know that that's an undocumented chain of calibrations, each contributing to the measurement uncertainty. And when we look at this, we see it starts with SI. Yesterday, I will share a story with you. It'll be quick. I was told I'm looking to buy another Agilent 3458A. I probably said too much now. If you have one and want to sell me one, I'm your ideal customer. Though I was told that somebody was an expert, and the first thing that they told me after I talked to the expert, they asked me if I needed NIST traceability. So that's the short story of it. But the long story of this is things are not NIST traceable, right? If you talk to NIST, Elizabeth Burnham is going to talk to you about this, and it's not. It's traceable to the SI through an NMI, recognized under the CIPM MRA. And I know Patrick has updated all of his certs to have this longer phrase on it, because Dilip told me, but this is the right thing to say. Is, I've seen people do it. It's traceable to SI through a National Metrology Institute. And if you really want to put NIST on there, you put such as NIST, recognized under the CIPM MRA. So, but the way uncertainty works here is you have your SI, and then for most parts, you have your NMIs, your National Metrology Institutes. Then you have primary labs, and that's where we're sitting here. And then your accredited cal suppliers, working standards, field measurement. And if you look at the uncertainty, it propagates, right? So if this is going to do a measurement at 4 to 5 parts per million, we can't be better than this. We have to absorb their uncertainty of the calibration. Then we add up all our uncertainties and do everything, and we're at 8 parts. And we do a calibration for an accredited cal supplier. Well, they're absorbing that uncertainty. And then they're at 0.2 and working standards 0.1, and that's just how it works. So here we're showing the adapters. There's a tension setup. There's the reference standard for compression. And I like this with uncertainty. If you go to the documentation and tools section, you can download our spreadsheet, which will just make your life so much easier when it comes to uncertainty. We also have an uncertainty guide for the UCM, but I like to think we start making it easy until we get to decision rules and tolerances and fun stuff that's often misunderstood. Now, the picture on the left, a lot of people see. You have your nominal value, you have your bias. The reason this is here is because if you're a lab that you like everything to read as close to possible as nominal, things drift off on you. And then a lab says it's intolerance, right? And a lot of the standards are written assuming everything is centered. They hardly ever are. So when we start looking at this, if somebody says to me, I need you to calibrate this device, and I want you to do an E74 cal, and I also want it to be within 0.05% of reading. And I say, what now? The standard's written so you use correction factors and coefficients. So you use these coefficients. They predict your curve. You should be dead nuts on everything. But then you find out that, oh no, they're reading it different. So that's a whole nother tangent of errors. What I want everyone to know is if you can correct for this bias, meaning using coefficients, you can reduce a lot of your error source that you may not be accounting for anyway. And the bias, the true way to evaluate this that people do not really understand as much is instead of bias, it's a type B evaluation of uncertainty. And then what you're actually measuring is your type A, like through statistical analysis. I'm throwing that there. This doesn't need to sink in for everybody right now. What needs to sink in is, hey, if I use the correction factor in the ASTM curve, my measurements can be, that nominal value can be centered, and we can remove a lot of that type B error. And if I use, here, I'm going to plug Morehouse because it's what we have. If I use one of our meters, the 4215 plus, or our new C705P, I can program in coefficients, use coefficients, and when I send that cal out, I can get my results. And then I can get a new set of coefficients that'll bring them right back in, and I don't have to pay for 2 calibrations, adjustments, and everything else. We also do this with computer software with the Hattie and regular 4215, but we now have 2 meters that have the coefficients built into them. So that gets us away from a lot of this stuff with tolerance. But I put it in here because I have a captive audience, and you need to hear my biased opinions on this, and or some good metrology practices. And when we talk about conformity assessment and TUR, a lot of people that buy the calibrating machine say, "Hey, I need to make a conformity assessment and say whether something passes or it fails." And then they start looking at like confusing TARs and TURs and everything else. And not going to go super high into it with this. We have other classes and videos on TURs and everything. But what all these standards wrote, the majority that I've read, I've yet to see one that doesn't have this, is they assume everything's centered. And if it's not centered, you have more risk. And the way to get you back to centered is the coefficients. So what am I saying? I'm basically saying, hey, centered on the left, no bias, your type B error is minimized. But on the right, maybe this is still in specification for our risk. We calibrate a customer's instrument, we pass it to them, then they use it in a standard in one of their machines. What are the odds, if your measurement's way out here, what are the odds that you're going to make a a decision that's going to be correct when your measurements are not centered. This is things to consider, things to ponder. I can tell you some of it. If you use a calibration provider with lower measurement uncertainty, you often have a lot more room to make that assessment. But if I make that assessment on the left and I give that to a customer and then they use that as the reference, unless they load that device consistently to 10,004 pounds or 10,004 newtons, whatever it is, unless they load it to 10,004 to generate 10,000, when they want to apply 10,000, there's an additional error. And I do not think people are doing this. So the best thing to do is use coefficients to correct it. Other than that, if we assign values and say, hey, at 10,000, it read 10,004, you want to apply 10,000, you need to load it to 10,004. Now, on the right, a calibration provider with higher uncertainty does the same calibration. Look at this. Same specifications, much higher uncertainty. They make a measurement at 10,004. If they're not doing conformity assessments or pass fail, they're going to pass you 34.47% risk. They're just going to give it to you. You're going to take it without knowing. And this is all the importance of having that calibration done by primary standards or low uncertainties, right? Because we can pass, if we do things right and we correct for coefficients and our measurements are more centered, or we correct for them not being centered, we pass less risk to our customers. And when we pass less risk, we make better measurements and we create a safer world. So when we look at measurement uncertainty, that bias, that type B, is often not in here. You're not even going to see it in here. Look, we read A2LA R205. We read some other documents. 5 R's in the E: repeatability, resolution, reproducibility, reference standard uncertainty, reference standard stability, and environmental factors. No mention of bias. However, I think it's NIST SOP 39 certainly does mention it and how to account for it and how to treat it. So you need to watch those type B errors that are here and that you could have. So again, what does a budget look like? We're going to do we're going to do this in a calibrating machine. At the end of the day, we're going to do, if we do E74, we could do an ISO 376, but this example is E74. That lower limit factor, we're going to have all of these, add them up, Morehouse reference CMC. This is an actual budget, and this was for the PCM machine. And look at our expanded uncertainty down there. And I really want my drawing tools, but if we look at it, it's near the bottom. It says expanded uncertainty, and it says 0.02% or 0.02234. So yes, it is possible and it is achievable, and those are good numbers. But there's a lot of things to account for. So if we use the primary reference standard, right, same, little bit different budget here. We switched off to a 10K with a primary standards calibrated in dead weight. This is 0.004%. Like the reference standard is 14.43% of our overall contribution to uncertainty. This is dead weights. Now we switch to secondary standards. Lab has a CMC of 0.04. That's a lot of secondary standard laboratories, maybe new technicians, all that stuff, cow machine. Same load cell being calibrated, but now that metrological traceability, what you have to inherit, the uncertainties at 0.04, 10 times higher, because 95.74% contribution to your measurement uncertainty here is with that reference standard. And when you used the dead weight method, or what we have here, it's 14.43. So you can get much lower uncertainties. And that's how the dead weights, and there's a easy picture to see the two different ones. Repeatability gets a little worse in these machines, but look, CMC 16.16, CMC 4, end of the day, one graph shows just a scatter of all of them. The stability of the reference standard is the largest contributor to the left, while to the right, the accredited cal supplier is dominant, not too much. Repeatability rears its head a little bit in there. All covered under our uncertainty. So if you're making primary, like I said, if your goal is to get the lowest measurement uncertainty possible, then I recommend going to NIST or an NMI. If your goal is to get the lowest uncertainty possible at a reasonable price point, then I recommend going to labs with primary standards. And if your goal is, hey, I don't need it, it doesn't matter, my measurements are not that critical, then secondary standards or some other ones. It all depends on what level you need. So a poll, if you want to answer it, what is the risk of not working with Morehouse? This is so biased to put these things in here. But again, look, we are 100+ years old and we support everybody. Like, people know, people that have dealt with us, Patrick, Tanner, that are on this, because you have questions, we'll help you. We help everybody all the time. A lot of unpaid consulting, but the goal is that we think if we do enough of the right things, that people will continue to use us and our products and our services, and then and the more we doubling down and tripling down on this, because look, customer service is just going to shit. It really is just not good for a lot of labs. You can't hire people when there's 0.6 people available for every job opening. You know, and we're faced with some of that too, where you hire the wrong people, and it's so problematic. And then the customer service falters. And then some other things, I'll get equipment that works, so other things will not matter. Uncertainties may not be calculated correctly. Well, obviously, uncertainties are a thing that I pride us on. Customer service uncertainties really pride us on that we're going to deliver good measurements at the lowest possible uncertainties that we can achieve. And we're going to account for things and the right metrological practices for ILAC P14, G8, and the other ones. So, but I'm going to open this up in a minute for questions if anybody has them. But there's guidance documents. Look, all this uncertainty stuff is, I know it's very difficult for some people, but we have a whole guidance document in here on how to develop an uncertainty budget for UCM. So if you wanted to purchase a UCM from us or have one, download this document. It's like a step-by-step guide. There you can see it on the right there, the step-by-steps. And we also wrote the guidance document for A2LA on force measurement uncertainty. G136, I believe, or G126 is their document. I wrote it, so I don't go to the website to get it. But it's they labeled it their G126. In common risk with most force calibrations, CMC values that are unrealistic. We find this all the time. I need to do a class on it where I have scopes that I've collected where the uncertainties are better than the CMC values are better than NIST. And now that Patrick's an accredited audit or works for A2LA as an auditor, he can go sniff those out and correct those where the CMCs are better than NIST. That's a fun one. Lack of understanding the standards, that happens. There are people that are on standards committees that just do things wrong because it's process-wise, they can do more calibrations if they just ignore it or take exception to it, even though the standard says things like in no case shall. It's like, well, no case shall, with the exception of when I do it because I want to do it quickly. Anyway, I add a lot of bias to these things. Not properly evaluating measurement risk or probability of false accept. Yeah, we report the PFA. That's probability of false accept. We use method 5 of ANSI Z540.3 handbook, and that's the most conservative method for guard banding because I am in a big debate with this, and it's people assume things are centered, and I'm more on the single measurement side of things, the bench level measurements, where I'm not evaluating our whole process uncertainty. I'm just evaluating the equipment you have sent us at the time, and therefore we use a very conservative method. Because we don't know. We don't know if you're switching pins, rotating pins. And then the lab does not, this is the biggest one here, the lab does not replicate how the instruments are used by using the right adapters. We ask these questions. We're not perfect with it, but we do a fairly good job. It's on my radar for next year to start simplify it for our customers. We have forms online, but again, if people don't understand it, they need their handheld a little bit more than just asking all of those questions that I rattled off. So, making better force measurements, Morehouse Force Machines. I like to think that we're one of the best with this. Using the right calibration provider, making sure calibration replicates how the instrument's being used by using the right adapters to ensure results are repeatable. Working with a company who can help you calculate your measurement uncertainty correctly. You know, if you help people, it's never a bad thing. Measurement risk and cares about the measurements you make. And then finally, when you ship things, there's a couple more slides here. Look, people that do not buy these cases are not cheap, but they're not super expensive. And the cost for what's on the left is far less than when you have instruments damage and you lose the stability or need repairs or you can't get your as received data. If you're not using control charts and process controls where before it leaves, that you know exactly how good your instrument was and you can validate it, you're in trouble if damage happens during shipment. How far back do you have to go? Do you have to go back to the last cal? Will you ever know if the instrument was good or bad? I mean, there's statistical methods that can help you, but it's still something that no one should have to deal with. So investing in the right shipping equipment, I urge people to do. And then lastly, it is this webinar was timed. It's November of 2022, and we have several machines. If you have the budget in left that you want capital equipment and wanted expense this year, we have a few 100K machines. We have several BCMs. That's the benchtop machine. It's a 10,000 pound portable machine. And then we have our 2,000 pound portable. We also have a couple scale presses. They're large if you want to get into calibrating aircraft scales, truck scales, or anything else. And we have, of course, load cells, meters. We inventory most of this stuff and have common stock, the new 4215 Plus and the C705P. What we do not have are regular 4215s because they had a supplier issue, but we have a lot of other things. And what we didn't talk about is the new C705P. That is a budget-friendly indicator that uses coefficients for field measurements. It's I wouldn't say it's metrology grade. It's on the cusp of being metrology grade, but it's really well suited for field applications for like E4 and 7500. And then the final one, if you want to learn Morehouse YouTube videos, I ask if anybody's wants to do me a favor, please follow us on YouTube. As soon as we get 1,000 followers, we can choose what videos and how they align for people, and so you don't watch one and then it goes off to something else. And we're close. I think we're like 100 some away. But we have videos on measurement confidence. We have free downloads on uncertainties. And then if you follow us on LinkedIn, that's an older picture. We're now at like 1,570 followers, and I want to get to at least 1,600 by year's end. So with that, I'm going to open it up. If anybody has questions, I'm going to stop the recording so you can ask your question and know that you're not being recorded.